All right, so our last lesson here this unit is our exponential and logistic models. It's not logarithmic, it is logistic. That's the new topic, that's the BC topic. We'll do the exponential ones first, then we'll take a break, then we'll do the logistic ones. So exponential model, it's going to be written in words like this. The rate of change, that's the derivative, the slope, of a quantity is proportional to the size of that quantity. So it's going to be dy dx. Or did I want to use t for this? You know what, let me use t, because usually that's how you see it in the problem. Do dy dt. So that's your rate of change is proportional to. So you're going to have k times the quantity, which would be y, whatever that is. And we're going to solve that differential equation. So it's the rate of change is proportional to however much you've got. So when they write that out in words in the problem, you need to go, oh, this is exponential. So moving the y over, that would be 1 over y dy, and then multiply the dt over, it would be k dt. And then we're going to do the antiderivative. So what do we get on the left side? Good, ln of y. And then on the right side, k is just a constant that could represent any number. We're doing the antiderivative with respect to t. So it would be kt plus c. We're trying to jam every letter of the alphabet into this problem, it feels like. All right, and then you're going to get y by itself. You can drop the absolute value. Like mostly these are real world problems. You're not going to have like negative amounts of stuff. So how do we get rid of the ln? Exponentiate. It's e to the power of. E is a number, c is a number. So we write that out front just as one great big constant. And you get c e to the power kt. Do you guys remember from pre-calc when we did compound interest?
Yes.
And you did that? And it's so funny because that's the lesson I taught today in pre-calc. But anyway, do you remember PERT? That's this. And if you want to write PERT instead of CACECT or whatever, like it's the same. Do you know what I mean? Like, why are we like, oh, let's just change the letters for everything? But this C is the initial amount. I mean, I'm going to write C and K because that's what we use in calculus. But if you want to write PERT, it's literally the same formula, same thing. And then K is the rate, which is why it almost makes more sense to use this because it's R for the rate. And P stood for principal. That's the amount of money that you were putting in the bank. Anyway. It's literally the same formula. It's not any different. We just changed the letters of the alphabet.
That would be how you find that formula.
Correct. Yeah, exactly. See, I've got doubling time and half-life. It's the exact same idea. In pre-calc, we do it for mostly money. We talk about compound interest, but you can use it for anything that grows or decays exponentially, like anything that is exponential. Yeah, so in pre-calc, you brought up a good point. That's where this comes from. In pre-calc, I just hand you the PERT formula and I go, here, memorize this. And no one asks me why, because you're all great students, you just do it. But this is where it comes from. I can't explain it in pre-calc though, because you need an antiderivative. And yeah, you can handle an antiderivative. Well, because you sit in here while I teach this class, so you probably sort of have learned some calculus just from sitting in here. Yeah. Okay. Number one, the rate of growth of bacteria is proportional to the number present. That's the sentence that should trigger for you, oh, this is exponential. That's what that means, right? There's 300 present initially, there's 700 10 minutes later. Let's write an equation. So it would be y equals C is 300 and then e to the power kt. We started with 300 bacteria. So put in that for the initial amount. Now we need to find k, that's missing, the rate. So we're going to plug in 700 for the amount of bacteria. That's going to be y. That's like the amount. 700 equals 300 e to the power k times, what was our time? 10 minutes. We're going to solve for k. So what would you do to both sides to start solving the equation? Not yet, but we will. Divide by 300. 700 over 300 be 7/3 e to the power 10k And then we're going to ln both sides to get rid of e. So you get ln of 7/3 equals 10k, and then divide by 10. So this is what you want to type in your calculator. ln 7/3 divide by 10.
There is an absolute value on the ln, but when you go to type in ln, if you use absolute value, like
where is an absolute value? Well, you would have to do it separately. You would have to get ln and then go into the math menu, into numbers, and get the absolute value. Like there's no button that'll do them both together. You would have to do it separately. Well, because an absolute value just turns things positive, I tend to just do it in my head. Like if there was a negative value, I would just type the positive value and not worry about typing an absolute value, if that makes sense. Did you get 0.084? All right, you must store that. I don't care what letter of the alphabet you store it as, but I usually do A. Store alpha A, enter. Store, which is right above on, so store alpha A, enter. Store alpha A, enter. Now we actually didn't answer the question. What is it asking for? Write an equation. So your equation is y equals 300 e to the power 0.084t. You just have to put it all back together, like reassemble it in order for it to be your final answer. It's like we found all the missing parts, but you have to put it back together to be an equation. Oh, and I made another part A. Haha, that should say B. Typo. Part B, what is the number of bacteria after 20 minutes? We're going to take 20 and plug it in for time and get your answer. So you will type 300 and then E. Do you guys remember how to put E on the calculator, where that is? Second ln, which is kind of like next to the 4 button. So you're going to do 300 second ln to get E on there. Do not type 0.084. What should you type? A, alpha A. We'll copy and paste it for you so that it will be the whole decimal, not chopped off. And then times 20. No, in this case, you can just put your answer. What did you guys get? 33.3 repeating. I'll just write 0.333 bacteria. You could have a decimal point of a bacteria, I suppose. Chop them in half. I don't feel bad for the bacteria. All right, doubling time and half-life. This is for growth, this is for decay. Doubling time is the time it takes initial amount to be twice as much. It kind of is what it sounds like, but the only thing people tend to forget is that it represents a time. Half-life is a time. The time it takes the initial amount to be twice as much. And half-life is the time it takes the initial amount to be half as much. So just remember that they represent time. And in the problem, it's going to say years or minutes or seconds or millennia, or what did I make the one, decades that one time? Remember we did nanometers per decade? Anyway, whatever the time is, it's going to say it in the problem, right? So number 2, an element has a half-life of 1,500 years, takes a long time to break down, initial amount of 200 grams, find the amount after 10,000 years. All right, so we're going to have y equals 200 e to the power kt. We know the initial amount is 200. What we don't have is k, so that's what we need to find. Now, it doesn't say how much is left over, but it says half-life. So hey guys, if you start with 200 and it's half as much, what do you end up with? 100. Okay, so even though it doesn't say it in the problem, we need to realize that's 100 equals 200 e to the power k times, what was the half-life? 1,500. And then we're going to solve for K. So divide over the 200, you get a half. Oh my gosh, the half-life is crazy. All right, equals e to the power 1500K. And then what? ln. ln of a half equals 1500K. Divide by 1500. So this is what you want to type in your calculator. I think this one comes out really small. I think it comes out so, because it's 1500. I think it comes out so small that it's in scientific notation. Yeah, do you get negative? Oh, why is the rate negative? Because the amount is decreasing, it should make sense, right? You get blah, blah, blah times 10 to the negative fourth. That's what this means, okay? 620 times 10 to the negative fourth equals K. It doesn't matter, just store it as A, store alpha A, enter, store alpha A, enter, store alpha A, enter. I'm just gonna say it over and over again so it gets stuck in your head. All right, find the amount after 10,000 years. So we're gonna have y equals, what did we start with, 200? 200, e to the power, I'm not gonna write all of this all over again. I have it stored as A, so I'm just gonna write A times 10,000. And that's what you're gonna put in your calculator to get your final answer. So 200 e to the power alpha A times 10,000. After 10,000 years, you'd think there wouldn't be a whole lot left. Did you get 1.968 grams? Good, I was just about to say, what are the units? Oh, and then this one is a compound interest problem. You put $500 in an account, so that's your initial amount. So it's going to be y equals 500 e to the power kt. And it takes 6 years to double. All right, so I know it doesn't say it on the paper, but if you start with 500 and you double it, you end up with 1,000. And when you divide it over, you're going to get 2. Spoiler alert. Right? 1,000 equals 500 e to the power k times what? 6 is your doubling time. And then you're going to solve for k. So divide over the 500. 2 equals e to the power 6k ln and then divide by 6. So you're going to put in your calculator ln of 2 divided by 6 . Somebody shout it out when you get it. I don't want to just like tell you all the answers. 0.115. Store it as A. So you can do a copy paste. Store alpha A, enter. Store alpha A, enter. How much money is in the account after 8 years? It would be y equals what? I'll ask you guys. How will we set it up? Yeah. 500 e to the power. Yeah, A, this 0.115, I'll just write A, and then times 8. 8 is the number of years that was given to us. All right, so $sign is your units for that, cash money. And that is what you will type in. All right, so the other model that we're going to look at is the logistic model. And what it has is a carrying capacity, which they call L, past which growth cannot occur. What this model is used for most of the time are populations. For example, and I'm going to use deer as the example because I made this one, I think, about deer. Yeah. So the environment can only support a certain number of deer. Otherwise, like if there are too many deer, they will use up all the resources and some of them won't survive. So that's like the carrying capacity, like beyond which the environment can't support any more deer. Does this make sense? That's kind of sad, but anyway, that's like an asymptote. I'm not going to actually solve this one for you. I'm just going to show you what it looks like. There's two ways that you can see the differential equation written. One of them is k times y, and then in parentheses, L minus y. The other one is k times y, and then 1 minus y over L. This bothers me. And I asked another Calc BC teacher about it because I'm like, these aren't technically mathematically equivalent. And his answer was like it makes sense, but it does still bother me. So if it bothers you too, I'm totally with you. K is an unknown constant. So you can fiddle with K if that makes sense and like still have a differential equation. The K, like you can multiply or divide by K because since it's an unknown constant anyway, does that make sense? Like it's sort of like kind of a crap answer. But anyway, sometimes you see it written like this and sometimes you see it written like that. And all I can tell you is you have to be aware that both of them are logistic because they might write it either way. All right, and again, we're not going to like separate this and work it out. I'm just going to tell you what the equation would equal. It is L over 1 plus C e to the negative k t. So the way that I kind of memorize that is, do you see how this part is C e to the kt just with a negative in it? So that's the same as the one we just did, and then there's like a few extra little parts to it. So anyway, these are the things that you'll need to be able to recognize. Yeah, that's an L. L is the carrying capacity. So that's where the asymptote is going to be. And I'm going to draw you a picture here in a second. All right, so if the amount, so like I was using deer as an example, if the amount of deer is between 0 and the carrying capacity, then dy dt is positive. It does make sense. If you're below the carrying capacity, you're going to be increasing the number of deer. They haven't reached that limit yet, so they're going to keep on increasing their population now. There's going to be more and more deer, right? If the amount goes over L, then the rate dy dt is negative. Again, that's when the deer start dying off. I'm just using deer as an example. It could be for any population, but if they go above that carrying capacity, like they're overusing their resources, then the rate of them is going to start to be negative because nature is going to balance it back out. So here's what this would look like. Is you would have this value L where there would be an asymptote. And your logistic model looks like this. And if you were to go above this asymptote, it would be decreasing. Like it would look, I don't like to draw that in because really you can't go above that, but it would be something like that. All right, this point right here is the inflection point. I tried my best to draw it. I'm not a great artist, but do you see how this is concave up and then this is concave down? That's your inflection point. It always happens at L over 2. So if you take that carrying capacity, divide it in half, that's where your inflection point is going to be. And the growth is always fastest at the inflection point. Because sometimes they'll ask that, where's the rate the fastest? And it's going to be at that point, and it's just L over 2. When y equals, let me write that out, y equals L over 2. Because this would be the t value, but we don't know what that is. You'd have to solve for that. So it's when y is L over 2. Is all this making sense visually? Like you have a carrying capacity, you divide it in half, that's your inflection point. That's where the growth is going to be the fastest. All right, try a few. Deer population follows this model. 40 deer were released initially. There are 104 deer 5 years later. So they're growing their population. Write an equation to represent this specific situation. All right, what is L? You should just be able to pull it out of the differential equation. 4,000, we can't have more than 4,000 deer, all right? So far, we can plug in 4,000 for this L value. It'll be y equals 4,000 over 1 plus c e to the power negative kt. Here's the bad news. C is not the initial amount. You can't just go and plug that in. Okay, but it's okay. We will solve it. 40 deer were released initially. Initially means that time is what? Time would be 0. So we're going to plug in 40 for the amount. That would be y. And we're going to plug in 0 for time. So that would be 4,000 over 1 plus, all right, let's see. If time is 0, e to the 0, the 1 times c is just c. So when you plug in 0, the rest of that kind of goes away. What would you do to keep solving this? This is like algebra here. We've got to, good, we're going to multiply that over. So 1 plus c is going to be on this side, and then you would divide by 40. They're just going to switch places. 4,000 divided by 40 would just be 100, and so c is 99. All right, we found c. Go up. What are we still missing? We found c. What's the other unknown? K. We still need k. All right. So we're going to use the other piece of information they gave us. There are 104 deer after 5 years. So we're going to put in 104 for the y value, that's the amount, equals 4,000 over 1 plus, all right, what did we just say c was? 99, e to the power negative k times 5 is our time. We recap what we did so far. We plugged in 0 for time and 40 for the amount, because that was the initial amount. Once we got c, now we're going back and plugging in this other piece of information to find k. All right, we're going to multiply all of this to the other side, divide over the 104. And we're going to have to pick up a calculator very soon here because this is getting beyond what I can do in my head. What would you do next? Subtract the 1. All right, let's do this in the calculator. Number 1, because I can't do it in my head, and number 2, because I'm running out of space. We're going to have 4,000 over 104 minus 1. I got 487 over 13. Is that good? Okay. Then what? I just subtracted the 1. What else do I need to move over? Yeah, divide by 99. So take that and divide by 99. Why is it doing it? I guess I don't really want it as a fraction. I kind of want it as a decimal. It's because I used the fraction bar there. Oh, well, that's fine. All right, so we have e to the negative 5k equals 487 over 1287. Almost there. Then what? ln. So I'm going to ln this 487 divided by 1287. There, now I have a decimal. I got negative 0.9718, and then last step would be divide by negative 5. All right, so I got that k is 0.194. Store that as a, store alpha a, enter. And we didn't technically answer the question yet because what did it ask for? What does it want us to write? The equation. So it's going to be y equals 4,000 over 1 plus, all right, c would come next. What was c, 99? 99 e to the negative 0.194 t. That is your final answer. Do you feel like that was a lot of steps? It was. We put in the carrying capacity, we had to work out c, and then we had to go back and work out k, and that was a lot of nitpicky algebra, but we have the calculator, so we're all good. Letter B, But, and did you guys all store this decimal as A? You need that stored because now we're going to use it over here. What is the deer population after 15 years? Or what are you going to do with 15? Yeah, plug it in right here. Okay, so it is going to be 4,000 over 1 plus 99 e to the power negative alpha A times 15. You're just plugging 15 into the formula. It is just a lot of button pushing. So you got to be careful. If you do 3 decimal points, that's okay. I didn't mind chopping up the bacteria. They don't really have feelings, but this is deer. So let's round to the nearest whole deer. So 629 deer. What's that? Down. Oh yeah, I see what you're saying, like a half a deer. Yeah, 628. You want to write 628? That's fine too. Let's say 629 deer. All right, find the limit as time goes to infinity. All right, so limit as t goes to infinity of this equation. Yeah, all of calculus relies on limits. Like a derivative is, like the definition of a derivative is based on a limit, and an antiderivative is a derivative in reverse. So it's like at the bottom of everything is limits. So as time goes to infinity, you would take an astronomically large number, multiply it by 0.194, it would still be an astronomically large number, but then you would make it negative. That would reciprocate this. So instead of being astronomically large, now it is astronomically essentially 0. This part goes to 0. So you end up with 4,000 over 1 plus 99 times 0, which would be 0. And so you get 4,000 deer. Why does that make sense that it came out to 4,000? That's the carrying capacity. Could you answer that without doing any work? Yep. It's just going to be that L value. Not for that, but look at this one. It says verify that L equals 4. So now since it says verify, you do have to show the steps. And you're like, why'd you make us write it for the last one in school? Because I want you to see where it came from. All right, verify that L equals 4. So we're going to do limit as time goes to infinity for this model right here. And as you make t astronomically large, it's negative, that's going to reciprocate it. So instead of being really, really huge, it's going to be really, really tiny. It's like you have a billion and then you flip it and it's now 1 billionth. It is essentially 0. So you get 4 over 1 plus 0, which is 4. We verified it, go us. All right, find the point of inflection. The point of inflection happens when y equals L over 2. Here's your carrying capacity, this asymptote, we want half of that. So it's going to be when y equals 4 over 2, which would be 2. Okay, that's the easy part. If you want the t value, you have to solve for it. So here's your equation. We're going to plug in 2 for y and solve that. You take the carrying capacity, divide it in half. That's the y value. That's like the output value. But if you want the input value, you have to solve for it. All right. All of this is going to get multiplied over. The 2 is going to get divided over. They're going to switch places. And 4 divided by 2 is 2. So you can just go ahead and put 2. This one's not as messy as the other one we did. It's not too bad. What would we do next? Okay. Subtract 1 and then divide by 2. So I'm just going to write it as 1/2 because I'm going to run out of space. We subtracted 1. 2 minus 1 is 1. And then we divided by 2. And then ln. And then divide by -3. So what you would type in is ln of 1/2 divide by -3. 0.231. So the inflection point is 0.231, comma 2. Humor me for just a second and let me show you what it looks like. I'm a real visual learner and I'm sure a lot of you are as well. Oh, crud. Okay, so our carrying capacity is at 4. And then where was this? 0.231. So like somewhere here and then at 2 is where that inflection point was. So this part's concave up and then this part's going to be concave down. So this is at 2 and then that carrying capacity is at 4. Does this make sense visually? Like, just want you to be able to see it as well. So this is the inflection point, and right here is our 0.231.